Well, as I said, I have been reworking all these instructions. They are now oriented correctly. We've done this the last time. And I've already done a lot of them on the left side. Now when I started to define a lot of registers already as well. Let us keep going with this. Six. That will be 7. But wait, yeah, 7 is out. We can see this here. And we will have to keep that in mind. So we are going to delete our 7. 6 is count, by the way. 0, 1, 2, 3, 4, 5, 6, 7. Count. Let us name it CNT. Is this 6? Yes, this is 6. And now let us define some more. Wait, at which point do we put our RAM? This is 4, 3, 7, 11, 15. RAM. Now it is time for 8. 9, 10, 11, 12, and I guess I'm gonna define the rest. I didn't even add them. This is so unfortunate. Oh, 11. I just didn't. Just didn't add 10. Whatever. Here we have it. Well, the registers just correspond to the binary, right? And now we are going to have a look at, as I promised, some actual assembler commands and ARM definitions. See, this is what I oriented myself on when I was defining the names for our instructions, right? EQ for equality, NE. Oh, I did NEQ instead of NE. Let's go with NE instead of, there it is, instead of NEQ. Or let us maybe let us keep both of them. And yeah, already also want to show you this piece, like this website. And on this website you can basically read this part, and I'm going to read it to you. An assembler is a program that translates symbolic code, assembly language, into executable object code. This object code can be executed with an, in this case, right, ATC51 compatible microcontroller. Like, these are instructions for the ATC51 instruction set, respectively architecture. The architecture that we have built is the LEG architecture, right? Which is this artificial architecture. And it is ours. The way we defined it is the way we defined it. So, if you have ever written a computer program directly in machine recognizable form, such as binary or hexadecimal code, you will appreciate the advantages of programming in symbolic assembly language. Yeah, and we actually have done this, right? Very early on. And if you remember the add 5 level, where we would take an input and add 5 and then output it. This is basically the moment in time where we were programming directly in binary. And now we later on had these predefined instructions that we could use, and then right here, and then we would be able to create our own little assembly code. And now we're at a point at the game where we created our own architecture, and we are able to define our own instruction sets, and not only that, but also define our own little assembly codes. Isn't that amazing? Yes. Assembly language operation codes, mnemonics, are easily remembered. For move instructions, add for addition, and so on. You can also symbolically express addresses and values. Values referenced in the operand field of instructions. Because you assign these names, you can make them as meaningful as the mnemonic for the instruction. For example, if your program must manipulate a date as data, you can assign it a symbolic name, date. If your program contains a set of instructions used as timing loop, executable, well, we're going to get to loops and stuff later on. This is going to be very fun. This is going to, I don't know, for me it was mind-blowing when I first discovered this, and I would love to show to you. Amount of time has passed until a specific, oh, interesting. You can name the instruction group timer loop. Contains a set of instructions used as timing loop. Specific amount of time has passed. Also name the instruction timer group. Yeah, interesting. I don't know if you can imagine how we would implement that. I guess you're gonna have a hard time imagining this, because, like, if you didn't play the game or don't know, if you're actually learning this stuff from me, or trying to get something out of this. We haven't defined jumps so far, so loops are going to be maybe a little bit riddling. Maybe you can think of a way. Yes, we defined add, and we're going to define move in a second as well. But first of all, Yes, here's some common assembly operators, which are in this case for AX51 operators, plus, minus, divide, less than, less equal, and these are basically these symbolic ones, right? We could also, I mean, the game, I think the game said earlier in its manual that it lets us do these kinds of, no, actually it doesn't let us do these kind of comparisons. Interesting. But it lets us perform arithmetic on our instructions. Wait a second. Plus, and, or. So it adds the values when we use a plus. So we would actually rather use this one instead of the plus, because this one is going to OR for us. Yes. Then we have this one, EQ. Is probably equivalent to, compares to the second and the first operand, and returns a value 0 false if the two operands are equal, or value 1 if true if the two operands are equal. If they are not equal, 0 if they are equal, 1. And it's basically the same for EQ. Greater than equal. These are mnemonics, right? High. What does high do? The high operator returns the high order byte of operands. 16-bit operand is assumed. Yeah, this is future music. Because sometimes with longer bit structures, we would sometimes split this whole, I think this is called a word, right? 32-bit word. This would be a 32-bit word, and you can split this into multiple parts, right? 16 high bits and 16 low bits, which would make it just 2 parts. Or I guess there are multiple ways of defining this stuff. So where have we been? Yes. An assembly program has 3 parts. Machine instructions. The machine can execute. Detailed discussion of the machine instructions is in the hardware manuals. Assembler directives define the program structure in symbols and generate non-executable code, data, messages, and so on. Assembler controls set assembly modes and direct assembly flow. And by the way, these are executable code, data, messages, and so on. Yes, these are basically given structures that we could define in our architecture, right? Just as we can immediate values in the architecture that we have built. And this is how I understand it. And a compiler would know how you would mark these kind of data structures, so it would know how to translate them into the correct bit structure. So the machine would then be able to interpret this. Hope this is understandable. Yes. And then we can have a look at some actual ARM instructions as well. I can provide you with these links. And also in ARM, you would not define the conditions separately, but add them to the operation that we want to perform. Just extend it, and then therefore create a conditioned operation, right? At least this is what it seems like. Registers. Okay, let's have a look at add, for example. This is add a mediate. Add a mediate ARM. Instruction adds an immediate value to a register value and writes the result to the destination register. It can optionally update the condition flag based on the result. Yeah, I have no idea why it says ARM, but what we can actually take from this already is that we write add in our assembler. Then we would give it a destination. An n, register n, right? This is our, you can take whatever register, right? And a constant, which would be the immediate value. Then we would have add register as well, which would take basically this form. Yes, we would write add. What does this S translate to? Oh, we can also have a look at how the apparently 32. Yeah, this is a 32-bit version of ARM, right? There is ARM7, the 32-bit variant. We can see that the highest three bits define the condition, right? Then we have a lot of empty stuff that isn't relevant to add registers. Yes, I wish there was a way to zoom in on this a little bit more. Rn is this is just, I don't know. In mathematics we use n and m for variables, right? Register n, register m, which define the two registers that we then add and put into our destination register. And we can also shift, right? This is interesting. This is optional, I guess. We can also shift. But what do we shift? I have no idea. Immediate, and there's ty. This is RM. So these 1, 2, 3, 4 bits define our first register. Then 16, 70, 40, 30 define the destination. And if we were to immediate a value, we would have 1, 2, 3, 4, 5 bits that we could use to immediate. I guess this is why it is immediate 5. Then we have this stuff. Sadly, I cannot explain to you right now. And yeah, basically it's not the lowest 4, the least significant 4, but rather 1 to the left, right? 0 would be on a different page, but the second, third, fourth, and fifth bit define the second argument. Let's see if we can figure out. Oh, and this is true for RMV 4, 5, 6, and 7. I guess we can have a look at this at a later time. All I wanted to show you is though how beneficial all of this is, and understanding and stuff like that. I find this to be really exciting. So let's go on. We defined a lot of our instructions. This is also, I don't know, that's why I love this game. This is so close to a 32-bit operand. Do we have no, we don't have a bit structure for this architecture, the AX51. Yes, so here we are. Having defined a lot of our instructions. Move. Let us implement move, right? How will we implement move? Move, we would we do it like this in our architecture. And the command move. We are gonna make it an add, right? We're gonna get gonna have to get a little bit creative, right? And then we do a calculation. And then we add. So this is going to be move, right? And the way we are going to do it is we're giving it the first argument. It's going to look like this: move R1. And since move is an add command, right? We will now say 2. R2, and what this will do is it will add the value which is the value of this instruction, which is 0, as we've defined it as 0, and yes, then we'll add 0 to the first argument and then save it into a destination, right? This is a great way to do it, if you ask me. So now we can move, we can add. I think we have all that we need to solve this level, right? So how do we do it? What even is the... Oh, we have to save to our RAM and 32 times. So we don't have to find our input, right? Input is 7. So we have to find our input. In and out is the same. Now we move input to register 1. No, we don't. Let us define, I think I said this already, let us define this one as our RAM address. 4, 8, 12, 16, register 15 as a RAM address. ADDR. So in the beginning of the code, there should be a 0, and now our RAM address. So what we will do is we move our input to RAM, right? The next thing we would do is we would add, and then we would mediate our second argument. We could define this as add I, right? I think this makes a lot of sense. Add I, add a mediate, and this would correspond to argument 2, right? We know that add is an empty byte. Add I, so we don't have to write this plus a mediate. Add I, then we would take the value that is sitting in RAM address, then we would mediate 1, and we put it back into RAM address. So, and then do this 34 times, 32 times, and then once we are done, we would move our RAM, move what is saved in our RAM to out. Are we supposed to move I 0 to RAM address? Move I would move an immediated value. Let us define move I. The first argument is the one that we want to mediate. Move 0 to RAM address. And then we would once more move RAM to out, add I, or DDR plus 1 into ADDR. Do this 32 times. So now we would have to make a check, right? Maybe we could also get values, or rather move 1. Or let's call it in loop, and let's call this one out loop. So if it is less than or equal to, we can do this, immediate the second value, less than or equal the value that is sitting in RAM address is compared against the 32. No, 31, because we have to keep in mind that the 0 is the thing. And then we jump back to out loop, right? And in this case, we do the same thing. I think this should work. Let's see. Does it work? No, it does not. But why doesn't it work? Oh, we made a mistake. This is unfortunate. Okay, but I guess I hope that you understand the logic of this code and what I showed you was beneficial to you. We are going to fix this in the next video. And yes, goodbye and have a good day.